Greetings and salutations, magical chemists. Let's talk about the glories of bonding. Well, as you probably know, the attractive forces that hold groups of atoms together are called chemical bonds. And bonds tend to form such that each atom has 8 electrons on its valence energy level. This is called the octet rule. And the goal of bonding is to achieve the greatest level of stability for the atoms involved, which means they want to be at the lowest possible energy state. There are 3 types of bonds that you need to know: ionic, covalent, and metallic. Now, ionic bonding happens between metals and nonmetals, whereas covalent bonding is when nonmetals and nonmetals bond. And metallic bonding, well, is when you have only metals. Because bonding properties and naming rules are so different between ionic and covalent compounds, it's essential to make sure you are 100% aware about the difference between ionic and covalent. So there is a quick mnemonic to help you remember. I'm on the CNN. So the first half, the I in I'm, tells you ionic, and then is going to be a metal plus a nonmetal. And then the CNN is going to tell you that covalent is a nonmetal plus a nonmetal. Okay, the focus of this video is going to be on ionic bonding. Now, ionic bonding happens when you have, so we say metals and nonmetals, of course, but the idea is that it's between 2 atoms that have very different electronegativities. And in ionic bonding, electrons are being transferred from the metal to the nonmetal. And so the actual chemical bond is that Coulombic attraction between cations, which have a positive charge, and anions, which have a negative charge. In their lowest energy state, ionic compounds form into these beautiful, basically array, this pattern of positive, negative, positive, negative. It's the greatest level of stability. So it is called a crystal lattice, or just a crystal for short. So you can define something called lattice energy, and that just means how much energy it takes to break apart your solid ionic compound. So let's consider the properties of ionic compounds. Well, that really strong attraction between positives and negatives gives them very high melting and boiling points. And because of the crystal lattice, they tend to be hard and brittle. They don't bend, right? You can't bend salt crystals. They just crunch and break. Now, it is important to recognize that if you have a liquid or molten salt, or if you have an aqueous salt, an ionic compound dissolved in water, it will conduct electricity, act as an electrolyte. This is because the charges are mobile and able to carry a current. However, solid ionic compounds cannot conduct currents because their charges are fixed in place. Let's remind ourselves about how to draw Lewis dot structures for ionic compounds. The idea is you are showing the elements after they have gained or lost electrons. So remember, your metals, because they are metals, are losing electrons, so the metal ion should always be naked. But the nonmetal, which is gaining those electrons to have a full octet, should always look stuffed with all 8 valence electrons. So let's go ahead and look at magnesium fluoride. First, we need to know what a formula unit of magnesium fluoride is. Well, we know magnesium forms an ion with a 2+ charge, but fluorine, forming fluoride, has a single negative charge. And so to balance the charges, magnesium fluoride is MgF2. So let's start off just by looking at the elements. There's 1 magnesium, so I'm going to put that one in the middle. Of course, neutral magnesium has 2 valence electrons. And then we have our 2 fluorines, so let's put 1 on each side. So in their neutral state, you will of course notice that neither has a full octet, and thus not achieving its lowest possible energy state. But look at that, each magnesium is missing an electron, and magnesium has 2 to spare. So what happens is that an electron from magnesium is transferred to each of the fluorines. And now we have magnesium with a 2+ charge. It lost its outermost valence electron, so its second energy level is full. It has a full octet, even though it looks naked. And fluoride, of course, gaining that extra electrons makes it isoelectronic with neon. So now everybody is happy. However, these are still charged ions. So to show they have charges, we have to put square brackets, and then you put the charge outside of the bracket on the upper right. And so that is what an ionic formula unit of magnesium fluoride looks like. Notice the positive in the middle and then the negatives on either side. All right, you are going to try the glories of gallium chloride. Whee! After you try it, go ahead and unpause the video so you can check your answer. First, it's important to find your formula unit, and then you can draw your ionic Lewis dot structure. Naked gallium, of course, will be in the middle, surrounded by our 3 stuffed chloride ions. And there you go. Okay, let's talk a little more about lattice energy. Now, lattice energy, of course, is the energy it takes to break apart an ionic compound. An ionic compound is held together by charges. So, guess what? This brings Coulomb's law back. Coulomb's law will never die. In fact, you can write the equation for lattice energy. It's just a variation on Coulomb's law. This particular time we're showing a K as our constant to make it an equality, but you don't have to. We're not going to do math with this again. We're just, again, going to be looking at this as a proportionality. So, the idea is that just like any other Coulomb's law problem, if you have ions that are more charged or smaller, so they're closer together, then you're going to have a greater attraction between them. This time, of course, we're not talking about the nucleus and electrons. We're talking about two separate ions, but same old Coulomb's law. So officially, lattice energy can be defined as the energy released when a solid crystal forms from separate ions in the gas phase. So it is, of course, directly dependent on the size of the charges and inversely dependent on the distance between them because it's Coulomb's law. In this case, though, for lattice energy, the ion charge is generally going to be more important than the size. So if you have a greater lattice energy, of course, by definition, that means it takes more energy to separate the ions, which is a stronger ionic bond. Well, stronger ionic bond means higher melting point, takes more energy to break you apart. But it means a decreased solubility. The idea is, if you want to dissolve something in water, the ions have to separate, and if it takes greater energy to separate them, they're less likely to dissolve. Okay, so if you notice, we can look at a pattern of ions. So they're all alkali metals hooked up with chlorine, so the chloride remains constant. But notice, as you go from lithium, tiny lithium, to sodium, then potassium, then cesium, hey, did you notice? You start with a really big lattice energy, because super tiny lithium, the distance is small, and then it's just getting lower and lower and lower. As the positively charged ion is getting bigger, the charges are further apart and thus less attracted to each other. So let's try a couple of quick practice problems. Okay, so here are 4 compounds: sodium fluoride, magnesium oxide, and potassium fluoride. You are going to put them in order of increasing lattice energy, increasing melting point, and increasing solubility. And when you are ready to check your answers, well, unpause the video. Okay, first thing you want to check is charges, because remember we said ion charge is more important. Okay, so we're putting them in order of increasing lattice energy. Well, I honestly think it's easier to start with the end, the biggest, because the one with the greatest lattice energy is going to be the one with the greatest charges, so that's going to be magnesium oxide. And then the one that's a little bit less than that is going to be the one that has, well, it's got 1 positive 2 charge, but then just a negative 1, so magnesium fluoride would be smaller. Now you have 2 choices. They all are +1. But remember the thing about size. Remember that potassium is 1 more energy level down than sodium, and potassium is bigger. So that means the smaller sodium ion is going to be more attracted to fluoride. So sodium fluoride is going to be the one next in line, which means the smallest is the one that has the +1 and -1 with the large ion, giving it a smallest lattice energy. So we start, if we put them in order of increasing lattice energy, I did that backwards, but it would be KF, then NAF, then MgF2, and finally magnesium oxide. Of course, if you want to put it in order of increasing melting point, that's the same thing. Because if you have a greater lattice energy, well, it takes more energy to melt you. For increasing solubility, however, is going to be backwards. Okay, one more quick practice. Free response. Would the lattice energy of lithium fluoride be larger or smaller than the lattice energy of potassium bromide? Explain in terms of Coulomb's law. Ooh. All right, you know what to do. You're going to try this problem, and when you are ready to check the answer, unpause the video. Okay, first we have to recognize that the lattice energy of lithium fluoride is definitely going to be bigger than that of potassium bromide. Why? Well, Coulomb's law says decreasing the distance between charged particles increases their energy of attraction. And honestly, both lithium and fluoride are smaller than potassium and bromide. And there you have it. These kind of explanations should feel very familiar after all of our trendy trends. Okay, just one more thing to talk about with ionic bonding, and it's the percent ionic character. Just means, how ionic are you? Well, the greater the difference in electronegativity between two bonded atoms, the greater their ionic character. You can also define covalent character. The more similar the two atoms are in electronegativity, the greater their covalent character. You may remember dipole moments. If not, we will review them more when we get to covalent bonding, but it's a measure of bond polarity. If you have a greater dipole moment, that means that you have a greater percentage ionic character because you're basically a greater difference in electronegativity. So they're represented by arrows, and they point in the direction of greater electron density. So let's go ahead and use this lovely provided table to answer these two practice problems below. You're just going to arrange the four molecules given in order of increasing ionic character and then increasing covalent character. When you're ready to check, you know what to do. Okay, well, clearly chlorine gas has the smallest ionic character because chlorine to chlorine bond is exactly equal. So then notice, of course, there's only one actual ionic compound here, lithium fluoride. So, of course, that's going to have the greatest ionic character. And then in between are the ClF and HF, just by looking at their difference in electronegativity. Now, of course, increasing covalent character, well, that's backwards. Okay, and just 3 quick multiple choice problems, because these kind of bonding questions show up as a lot of multiple choice problems. So go ahead and try these beautiful problems, and then we will totally check the answers in class. Gasp. Yes, in class. I'm not going to give you the answers. Is that terrible? Maybe, but it'll be okay. All right, you are ready for our next video, on to metallic bonding. I'll see you there.